Assalamualaikum. The topic which I am going to present right now is the brief introduction about the carrier transport phenomena, and this is transport phenomena that is to be well defined in semiconductor devices. So we should know about the how the carrier is going to be transport in your semiconductor devices. I'm Fakra Kapoor, I'm PhD scholar. I am going to give you the brief introduction about those transport phenomena. So this would be the layout probably of this presentation. So what we should know about the carrier transport phenomena, that what are the carrier transport phenomena, and then we will discuss about the drift of the carriers, in which we should know about the mobility, what is the mobility, how the carriers are going to be conduct, and how the velocity saturation is going to be achieved in your carriers. And then we will going to discuss the another transport phenomena, that will be the diffusion process, diffusion phenomena. And in diffusion we are going to mention about the diffusion current density and the total current density that is going to be propagated with the drift and diffusion both. Then we will discuss about the Einstein relation, that is going to develop the relationship between the diffusion and drift. Then we will have an application of those carrier transport phenomenon, that is the well-known effect that is known to be Hall effect. Carrier transport phenomena should be discussed in details. What are the carrier transport phenomena? The net flow of the electrons and the holes in any semiconductor device that is going to generate the current in that particular device, and the process by which these charged particles, like for example electrons and holes in semiconductor devices, are going to move in particular device, is called the transport. And so there are the two basic transport mechanism in a semiconductor crystal. One is drift and another is diffusion. Drift is basically the process in which charge is going to be moved due to in the presence of some electric fields, and diffusion is the process in which the charge is going to be flow due to the density gradient from low to high or high to low. So another is the carrier transport, that is going to be determine the current voltage characteristic of the particular semiconductor devices. Let's briefly describe the carrier transport phenomena. And there are the two transport phenomena that we are going to work on. One is drift and another is diffusion. As we know about the drift, like your movement of carriers are due to the electric field. For example, they are going to generate some current when electrons are going to move in certain electric field. So you're going to have a current out of it. So how you are going to calculate the density out of it? Obviously, this is going to have some cross-sectional area where your charges are going to move in certain region. So you're going to have a current density in this region. So we can define it as J is equal to I over A. Just need to put all the values of your current definitions into your current density. So you're going to get the charge current density or carrier current density, and that is going to multiply it with your velocity of your carriers. Either they are electrons or the holes. So you're going to get the density in terms of charge carrier density times drift velocity. So we can say, like, we can define our, what should I say, the volume charge density for each carrier by just putting the values of charges. For example, we are going to just substitute the values of holes and electrons in this equation to get the values of our volume charge densities in terms of drift velocities. So this is all about the drift transport phenomena. Like, what are the features of our diffusion transport phenomena? Obviously, the carriers are going to flow due to the density gradient. Like you can see, there is a divider. If your electrons are going to move, just forgetting about the divider, so your current density, your electron density is going to decrease in this region, and that is getting increased in this region. So they are going to move in such a way that your electronic concentration is going to decrease in one region, and that is going to be balanced on the other side. So this is how the diffusion is going to work. Okay, like how the carrier drift is going to work. We know, like, our holes are going to accelerate due to our electric field that is established due to our battery. All the charges are going to have a collision with their atoms that are present inside the crystal. So they undergo some scattering process, and in this process they charges, for example the electrons in the holes, are going to loses most of its energy, and then it accelerates those charges, fine. So this all phenomena is going to get the average drift velocity of those holes in terms of their electric field. For example, you can see, for example, we have a setup like this, and if you are going to apply some electric field in a certain cross-sectional tube or in a certain rectangular box. So electric field is running in this way, and obviously current is running due to those electric field by having the drift velocity of those charge carriers due to this potential barrier, and those holes are going to accelerate, and obviously they get some forces by which they are going to be accelerated in certain direction. So the force measured due to those holes acceleration is just by substituting the Newton's second law to get the force in terms of our electric field. And we know like m static is going to represent the effective mass of our holes. So this is how the charges or holes are going to accelerate in certain electric. Okay, let's talk about the drift current density. Like we calculated already the volume charge density for our electrons and the holes. Now we are going to define our current density with the help of our drift velocity. As we know that current can be experienced by the total charge in certain crystal material, and we are going to divide our charge with time that is going to require to travel our charges to move from one point to another point. So for example, if we are going to write the electronic charge density, so how we are going to write? We are just going to write it as electrons are going to have a negative charge, so I'm going to write minus E times N is the concentration of your electrons, and V is going to represent the drift velocity of your electrons. So this is how the current density should look like. So I'm just going to write is on the similar basis with the hole density. So this should be written in this form like this way. I'm just going to replace minus E with plus E. I'm just going to replace the electronic concentration with the electronic concentration with my hole concentration. So as we know, our drift velocity can be represented in the electric field by this equation. We're just going to replace all those values into this equation, into the red equations. So we are going to get the drift velocity in terms of our electric. So if we are going to write the total current density that is developed due to the electrons and holes as well, we just need to sum all those densities. So this is how our equation for the total current density should look like in terms of our electric field, where N is going to represent the electron density and P is going to represent the hole density. Now a little bit about the mobility, like what is mobility and how it is going to be developed in certain crystal. As we know that force is basically the mass time acceleration. Acceleration is written as rate of change of velocity. So we are just going to replace it with the holes and electrons as well, and this is equivalent to our charge times electric field. We know like how the drift velocity can be it can be explained, like we just need to put the drift velocity in terms of our electric field like this way. So we are going to get drift velocity with the help of mu factor, and this mu factor is going to represent our mobility, and this is exactly equal to charge times the tau, that is the time developed during the collisions, and m is going to represent are the mass of the electrons and the holes, and E is simply the electric field. So this factor is going to represent as the mobility. So in generally I can write the electronic mobility in terms of time that is required to have some scattering collision, and I can write it simply in the general expression like this. And I for sure I can write the holes, for holes I can write the drift velocity in terms of my mobility like this way, and this mobility is for the hole can be written in on the same basis as I have written for the electron. So this is all about if we are going to develop the graph between our velocity and electric field. So generally the velocity is proportional to our electric field, but there are some charge carriers that can drift when you are going to increase the electric field in such a way they can saturate at high fields. So you're going to have the velocity saturation region by near the all the electric fields that are very high, just having the critical value of electric field by which you're going to have the saturation velocity and at that region. Now a little bit about the mobility effect with the carrier transport phenomena. Like we know, for example, your charge carriers are moving in certain crystal and they are going to undergo some collisions. So how they are going to move? They are going to behave in a scattering way, like they are going to move randomly from one point to two to three and four, and you're going to get the net electric field as zero. So the random motion of your carriers without the applied field, for example, you're not going to have any electric field. So they are going to generate some random phenomena. So you're going to have no net carrier displacement. So we know like our thermal energy should be equivalent to our 3 by 2 times of kT, because we are going to have 3D motion. So this is about 6.2245 exponent of minus 21 joule. This is very small. So what about like if I'm going to apply the electric field on that crystal, so what is the net effect on that crystal? So you can see like firstly they are moving in this way, but when I have applied the electric field, so their path is going to change in this way. Fine. So I'm going to get the net displacement in that case. Fine. So net carrier displacement is going to generate some net velocity. So according to electric field, I'm going to have some velocity of my carriers, or and this velocity is called as drift velocity by just applying the electric. Now we will talk about the temperature dependence of our mobility, like how temperature is going to affect our mobility of carriers. We know like for there are phonons and there are some lattice scattering. Atoms are continuously in the thermal vibration, and in return there is some disruption in the potential function, and this disruption of potential function would finally generate some interaction between our electrons and holes and the atoms that are vibrating along some lattice atoms. So we know like our mobility is directly proportional to the temperature that is of power of -3/2. So this is how your mobility is going to affect. And there is another phenomena like if you're going to have a ionized impurity scattering, so how your temperature is going to affect your impurity atoms. Firstly, they are going to be added into certain crystal. Obviously, that crystal is going to made up of some kind of semiconducting material, and these impurities are then ionized at room temperature, and these ionized impurity atoms have some interaction between their electrons and holes, and they are going to develop some ionized impurities. And obviously the ionized impurities are going to generated due to some concentration of your electrons and holes. And we know like there is some concentration of ionized carriers that can be represented as donors and acceptors. So I'm going to write the net concentration of my ionized impurities as Nd plus plus Na minus. So these ionized impurity atoms are have the inverse phenomena with my mobility, and they're directly pushing to my third root of my temperature. So this is how the temperature is going to affect my mobility. Now the mobility of electrons and holes, how for example I'm going to get the silicon material and I'm going to get some electron and hole mobility for this silicon material. So how I am going to get it? Like you can see in the graph, the electron mobility is higher as compared to your hole mobility. So for example, at lower level of your doping, the mobility is solely due to your lattice collision. But whenever you're going to increase the doping levels, so your mobility is going to increase, and that is only due to the scattering phenomena. Now we are going to calculate the scattering time that is going to generate our mobility. So for example, the scattering time or for my crystal, for example, for electrons, and how I'm going to get it, basically I'm going to get the probability for my scattering events. So dt is going to represent me the differential time, and tau is the total time. So this is the mobility time, and this is the latest ionized mobility time, and this is my latest vibration. So this is impurity time, and this is latest vibration time. So I'm going to add those two times by taking the probabilities in such a way I'm just going to substitute my values of tau in this region. So I'm going to get the mobility, the net mobility, that is going to look like this. So 1 over mu net mobility is equal to 1 over mu L, that is generated by your ionized impurity atoms, and 1 over mu L is going to represent you the mobility that is generated by your lattice vibration. And we know our proportion of temperature with this. So this is the graph of certain impurity scattering and lattice scattering atom, how they are going to relate. So that's all. We are going to cover the remaining part in the next lecture. Thank you so much.